Hi folks, we're going to take a look at the solution to number 16 on page 157. So here's the question. They give us a sheet of metal, and with that we have to create a rectangular box, and we do that by cutting out squares on each corner and then lifting up all the flaps. Okay, and what they tell us about this sheet is that it's twice as long as it is wide and has an area of 800 meters squared. So notice here, they don't give us the actual dimensions of the sheet. Okay, so we'll have to hopefully use our diagram to figure out how we're going to solve this. Okay, so let's start with a diagram. So we have a sheet and it's twice as long as it is wide. Okay, so if this is the width, then the length is just going to be twice that. Okay, and we know we're cutting off squares on each corner in order to create the box. Okay, but we really need some numerical information to help us come up with some formula for the volume, because we're going to need the length, the width, and the height of the actual box. Okay, so what we're going to do is we're going to take the fact that we know that the length and width have this relationship, okay, and the fact that we know the area of the total piece of metal is 800. So the area of this whole sheet of metal is just the length times the width, so 2W times W, and so now we can solve for W. Okay, so W squared is equal to 400, and square root of 400 is just 20. Okay, so it means this total length is equal to 20, and that means this one is equal to 40. Okay, and now I think we can set up our equation. Okay, so what we're looking for is the volume of the box. That's what we're trying to maximize. So we know that's going to be the length times the width times the height. So the length here is just given by 40 minus 2 of these little sections that we're cutting off. So let's call this x, and since we know we're cutting out squares, it's also x on that side. So the length of the box is just going to be 40 minus 2x. Okay, the width of the box is just going to be 20 minus 2x. And the height of the box, well, remember what we're doing is we're lifting up this flap here. So the height of the box is just going to be given by x. Okay, and there's our model. Okay, and let's just find a constraint on the variable. Well, here, if you sort of think that, you know, this is x, notice I'm working with the smaller side. At the very most, x can be, you know, half of that length there. Okay, in fact, it has to be strictly greater than half. So x here is going to be between 0 and 10. Okay, so notice how you have to work with the smaller measurement as opposed to the larger one to get that maximum possible value. Okay, so now let's do the calculus portion. Okay, I'm definitely not going to use a series of product rules here. I think it makes much more sense to multiply this out. Okay, so what do we have? We have 40 times 20, so that's 800 times x. So we have 800x. Then we've got negative 80 minus 40, so that's negative 120x plus that other x there, so minus 120x squared. And then we've got 4x squared times x, so plus 4x cubed. Okay, and this will be much easier to differentiate. So v prime is going to be given by, and I'll just write it in opposite order here. So this is going to be 12x squared. Okay, this is going to be minus 240x, and this is going to be plus 800. Okay, and we have to solve this equal to 0 to find our critical points. Now, I'm not even going to bother factoring this out and trying to see if I can factor by two binomials. I'm going to go straight to the quadratic formula. Okay, so that's negative b, so it's going to be 240 plus or minus. I'll calculate that with my calculator over 2 times 8, which is 24. So I'm just going to calculate that straight off here. Okay, so what do we have? We have b squared, so 240 squared minus 4 times a times c. Okay, and we'll take the square root of that. Okay, and so here we have 138.6. Okay, in fact, I'll keep that here. So they're both going to be positive. So let's see which one. Let's see if either of them are in our interval. Okay, so we got 240 plus 138.6 divided by 24, and that's 15.8. So we know right away we're excluding that because it's not in our domain. Okay, and now let's do 240 minus 138.6 divided by 24 is 4.2. Okay, so this is within our domain. Let's make sure that that indeed does give us a maximum. Okay, so remember that we're only interested from 0 to 10. We have our critical point in there, 4.2. But in order to draw this diagram, I'll put in that other critical value there of 15.8 because this is just a quadratic, so with a positive leading coefficient. So there we go. This is going from positive to negative in this interval. So 4.2 is indeed an absolute maximum in the interval 0 to 10. Okay, so now we have our calculus information. I'm going to go back and look at the question and see what they want. And it says find the dimensions of the box. Okay. So we know that x represented the height of the box, so the height is 4.2 centimeters. Okay. The length of the box was given by 40 minus 2x. So the length is going to be equal to 40 minus 2 times 4.2, so 31.6 centimeters. And the width was given by 20 minus 2x, so 20 minus 2 times 4.2. 11.6 centimeters. Okay, and there's our answer. So just a quick recap. So this is the type of problem we've seen before, you've had in the homework. The one little difference here was they didn't give us the dimensions of the sheet of metal. We had to use the area and that relationship between length and width to find the dimensions of it. And then from there, it's solved exactly as others have been. Okay, that's it for this one.